Good morning, ma'am. My name is Teen Industry. I am from CSCB section. My roll number is 234G105B1. My CIU2 topic is Cook's theorem. In this video, we discuss about the what is Cook's theorem, how we implement a Cook's theorem, what are the applications, and what is the conclusion of Cook's theorem, how we implement. Shall we discuss in this video? Let's start the video. First, contents. Cook's theorem, Introduction to Computational Complexity, the concepts of NP-completeness. We will discuss these contents in this video, proof of Cook's theorem, implementation, application, and finally we discuss about what is the conclusion of Cook's theorem. Let's move on. Cook's theorem. What is Cook's theorem? Exploring the complexity of NP-completeness. Cook's theorem, a fundamental concept of computational complexity theorem. Cook's theorem is known as fundamental concepts of computational complexity theorem. Establishes the extension of class of problems known as NP-complete. The theorem has profound implication for our understanding of limits of computation and the difficulty of solving certain types of problems. Introduction to computational complexity. First, classification problems. Time complexity. Third one, complexity classes. First one, classifying problems. Com computational complexity theory focuses on classifying problems based on the resources needed to solve them. In the classifications problem, we have to focus on the only classifying problems based on the resources we need to solve them. Next one is time complexity. The most common resources considered are time, number of steps, and space, amount of memory. In this Cook's theorem, we consider the time and space complexity. Time complexity is based upon the number of steps, and the space complexity is based upon the amount of memory. Third one is complexity classes. Complexity classes problems are grouped into complexity classes based on resources requirement. In the complexity classes, these problems are depending upon the resources requirement. Next one is defining P and NP problems. P problems first. Problem solvable in polynomial time, meaning the time required to solve the problem increases proportionally to a pro proportionally to polynomial function of the input size. In this P problem, the problems are solvable by polynomial time, meaning the time required to solve the problems. There will be increasing the proportional polynomial function input size also. In NP problem for which a solution can be verified in polynomial time. In the problem for which the solution is verified in polynomial time. However, finding a solution may take exponential time. Next, concepts of NP completeness. First one, hardness. Second one, reducibility. Third one, implication. First one, hardness. NP complete problems are the hardest problems in NP. In NP, the NP complete problems are hardest problems. Reducibility. Any problem in NP can be reduced to an NP complete problem in problem polynomial time. Implication. If a polynomial time algorithm is found for one complete problem, it will be solved all problems. In implications. Next one, Cook's theorem and significance. Cook's theorem. Here the formula for Cook's theorem, F3 is equals to A2 plus U integration is equals to the not equal to 1 is less than h. Existence of NP complete problems. Cook's theorem proves the NP complete problem exists. The first NP complete problem, the Cook's theorem identified the significant problems SAT. STAT means statement as the first NP complete problem. Foundation for complexity theorem. Cook's theorem laid the foundation for field of computational complexity. Proof of Cook's theorem. This satisfiability problem. The satisfiability problem, SAT means statement. We can write a statement in short form SAT, S-A-T in capsule. Is a problem in Boolean logic where the goal is to be find an assignment to truth values, true or false. Boolean means true or false. We can represent it to variable Boolean formula such as the formula evaluated to true. Cooks proves that the SAT in NP complete by showing the any problem NP problem in NP can be reduced SAT in polynomial time. Implications of Cook's theorem. P versus NP problem. Cook's theorem highlights the fundamental questions of whether P is equals to NP or P does not equal to NP. Practical consequence. Many real-world problems are NP complete, making them extremely difficult to solve optimally. Approxim Approximation algorithms. For NP complete problems, so approximate or used to find solutions that are close. Practical applications of theorem. Optimization problems, scheduling, routing, and resources allocation or NP complete problems. Network designs, designing communication networks, transportation systems, and power grids involves NP complete theorems. Cryptography. The security of cryptography systems relies on the hardness of NP complete theorem. Next one, limitations and challenges in solving NP complete problems. Exponential complexity. Finding optimal solution for NP complete problems typically requires exponential time and resources. Heuristic and approximation algorithm and the heuristic provides practical solution but do not guarantee optimally. Further research. Active research aims to develop efficient algorithm, identify problems, specific solutions, and understanding the relationship between P and the NP. Conclusion and further directions. Cook's theorem realized other understanding of computational complexity and its implication for solving real-world problems. Cook's theorem we use it to solve the real-world problems, while solving NP-complete problems remains a challenge. Ongoing research continues to explore new approaches and deepen our understanding of the limitations of computation. Thank you, and thank you so much for listening my presentation.